All right, lads and ladies, welcome back to Calc 2. Today, we are going to push a little bit deeper into our study of parametric curves. And I want to revisit the tangent line min-max thing a little bit. That felt kind of rushed when we went through that the other day. Kind of attack a few easier examples, make sure that we're all comfortable with that. And then we're going to talk about how to find areas bounded by parametric curves. So we're going to kind of do all of the Calc 1 stuff, but in the context of parametric curves. And then next time, or maybe a little bit today if there's time, but mostly next time on Monday, we're going to introduce the concept of arc length, which will eventually lead us to something called surface area. Both of those are what they sound like, but before we can even begin talking about them, I want to make sure that we're genuinely comfortable with tangent lines and regular old area. So this is MAC 2312, section number 004, which means this is a Calc 2 class, and the date today is the 8th of April, 2022. As I mentioned today, we're doing calculus with parametric curves. Which is section 10.2, and really this is kind of a part one. Specifically, we're going to talk about finding tangent lines. Mins and maxes. And the one example we did on Wednesday was a min-max example, but I feel like we need to revisit that topic and kind of warm up to it a little bit. That was a particularly challenging example that came from the cycloid. So we're going to revisit that. And this is really about finding horizontal and vertical tangents. So I'm going to explore a little bit with you this idea of where these mins and maxes come from and why in the setting of parametric equations. And the last thing we're going to do is talk about finding areas bounded by parametric curves. Because the area problem here, while it's not especially exciting, it is insightful, maybe, to look at in this context. It can kind of help you understand the early part of the class a little better, I think. So let me begin by saying, recall, the slope of the tangent line to a curve y equals f of x at the point, say, a comma f of a, all right, which is a point on the curve, y equals f of x, is found via the derivative m tan, which is the m sub tan. I'm going to use this as the m for slope and tan for tangent line, is the number f primed of a. And that notation works really well in the context of Calc 1, where your curves are all coming from a function. But there was another notation that you learned back then, often called the Leibniz notation, dy dx. The issue here is that dy dx, this is f primed of x, not f primed of a. So if you want to use that notation, we need to say we're going to take this derivative and evaluate it. This vertical line in mathematics just stands for evaluated at x equals a. Right, so this is the underlying framework from Calc 1 that we're going to build upon. In the context of a parametric curve, the difference is that we don't have y being f of x. Nor is x a function of y. However, by the chain rule, if x is x of t and y is y of t, really what we're appealing to here is something called the implicit function theorem, or you can think of it like we're implicitly differentiating. I won't go into the details of the implicit function theorem because it's a little bit over this class in terms of complexity, but you can use the chain rule to say that dy dt should be equal to dy dx times dx dt. And it is from this relation that we get the formula we used last time, which is that dy dx, the thing that we understand gives us the slope of the tangent line, is equal to the ratio of time derivatives dy dt divided by dx dt. And this was the formula that I gave you guys on Wednesday. I suppose I should put that dx dt in parentheses as well. The difference here is that in Calc 1, your dy dx was a function of x, right? When you had like y equals x cubed or something. And when you calculate dy dx, you get 3x squared or something. You get this thing as a mess of symbols involving the letter x. Here, because dy dx is calculated as dy dt over dx dt, and both x and y are functions of t, this thing is going to have t's in it, not x's. So I'll say here, though, dy dx is a function of t, not x. So when you go to do things like find tangent lines or find mins or maxes, you're going to be working with an expression involving the variable t. And because t is the parameter in parametric equations, we think of it as being like time, the t value doesn't immediately tell us the point on the curve. So there's sort of an extra step here of either finding the point on the curve, or if the point is given to you, finding the t value associated with that point. So I want to look at just one very simple example, and then we'll ratchet it up from there. Okay. So let x of t be 2 cos t and y of t be 2 sine t, where 0 is less than or equal to t is less than 2 pi, be our parametric curve. And let's find the tangent line. So find the equation of the tangent line to the curve at the point. Let's do, we'll do root 2, comma, root 2. Okay, so sort of two flavors of problems like these, where you're asked to find a tangent line to a parametric curve. Always you'll be given the parametric equations. Sometimes you'll be given the point on the curve. Other times you'll be given the t value corresponding to the point on the curve. And like I said a second ago, if you're given the point, you'll need to find the t value to go through some of these steps. If you're given the t value, you're going to need to find the point to go through some of these steps. Both are needed, and it's very rare that you're given both. So you're either given the point or the t value. Whatever you don't have, you're going to need to find. We'll get to that. But first, I want to go through the main sort of mechanical steps here. So I'll say we know that the slope m tan comes from dy dx, which is dy dt divided by dx dt. So I need to find dy dt and I need to find dx dt. Y along this curve is 2 sine t. So dy dt is the derivative of this taken with respect to t. That's 2 cos t. And x is 2 cos t. So the other sort of piece of this recipe that I need, dx dt, is the derivative of this taken with respect to t, which is negative 2 sine t. Therefore, dy dx is going to be dy dt over dx dt, which is 2 cos t divided by negative 2 sine t. The 2's cancel, the negative pops out, and cosine over sine is cotangent. So this is the negative of cotangent of t. And you see what I'm saying, where dy dx now, this doesn't have any x's in it, it just has t's. So if I want to find my slope, m tan, I need to plug some t value in here into dy dx. The question is, what t value do I plug in? So now I need to find the t value associated with the point root 2 comma root 2. I'm going to draw the curve in just a minute, but I want to show you how to find that t value even if you don't have the curve. So remember, this is an x, and this is a y. So if I want to find the t value at that point, I know that x is 2 cos t and y is 2 sine t. That means I need to solve the equations root 2 equals 2 cos t and root 2 equals 2 sine t. And really, you should think of it as a system of equations. You need both of these things to be true simultaneously. And this is equivalent to saying root 2 over 2 is equal to cos t, and root 2 over 2 is equal to sine t. And that first equation has two solutions. Where is cosine of t equal to root 2 over 2? Well, that's at pi over 4. And 7 pi over 4. I'm paying attention to the interval 0 to 2 pi because that's what my t interval is. So there's infinitely many solutions here if you let t go from negative infinity to infinity. But from 0 to 2 pi, these are the two solutions. The second equation also has two solutions on the interval 0 to 2 pi. The first one is t equals pi over 4, and the other one is t equals 3 pi over 4. That's where sine is equal to root 2 over 2. And because we're thinking of this as a system of equations, we know we need to take the t value that solves both of them simultaneously. So our t value is t equals pi over 4. Everybody see how I'm selecting that? I'm taking the one that solves both of these. Because at my point, root 2 comma root 2, both x and y are equal to root 2. So I set both x and y equations equal to the coordinates of those points. And then I take the t value that makes both of those things true. So there's a question in chat. Yeah, I'll take a look at this again. At the end, I'll draw the picture for you, and we can see sort of where those other solutions come from and why we knew to take these from the geometric perspective. But again, what we're trying to do is find the t value on the curve that puts us at this point. Remember, the way parametric curves work, every t value gives you a point on the curve. Remember, the very first day we made tables, right? Every t value gave me a point on the curve. I'm trying to find the t value that puts me at the point root 2 comma root 2. So I set x equal to the x coordinate, which is root 2. That gives me this equation. I set y equal to the y coordinate, which is also root 2. That gives me this equation. Each of those equations have two solutions on the interval 0 to 2 pi. And I take the solution that is common to both. So I know when t is pi over 4, the x coordinate will be root 2. I know when t is 7 pi over 4, the x coordinate will be root 2. Okay, that doesn't quite get me there, so I look at the y coordinate. I know when t is pi over 4, the y coordinate will be root 2. And I know when t is 3 pi over 4, the y coordinate will be root 2. So when are both the x and the y equal to root 2? When t is pi over 4. That's when both of these are true. That's when both of these are true. We'll look at it from the geometric perspective also. Well, let's go ahead and finish. We're almost done. So the slope of the tangent line, we know, should be dy dx evaluated at the t value that we found here. And since dy dx was negative cotangent t, dy dx evaluated at t equals pi over 4, that's the negative cotangent of pi over 4. What is the cotangent of pi over 4? Yes, very good. That's 1. So this is negative 1. Okay, the work is all done. To find the equation of a line, you need 2 things. You need a point on the line, and you need the slope of the line. The point on the line was given. We were told to find the equation of the tangent line to this curve at the point √2, √2. And through the work we just did, the slope of the tangent line is negative 1. So to finish up, we use the point slope formula, which is y minus y naught equals m times x minus x naught. Tell us that our tangent line is y minus the y value at our point, which is the square root of 2, equals m, the slope of our tangent line, which is negative 1, times x minus the x value at our point, which is also √2. So that's it. That's your final answer. I do think it's wise to illustrate this. So let's sketch the curve and tangent line from the previous example. We know that our parametric equations there were x equals 2 cos t and y equals 2 sine t, which means x squared plus y squared is 4 cos squared t, right, the square of x, plus 4 sine squared t. Which is 4 times cos squared t plus sine squared t. And since cos squared plus sine squared is 1, we get x squared plus y squared equals 4. So this is the regular xy equation for our parametric curve, and this is a circle. With radius 2, centered at the origin, 0, 0. So I can sketch that curve. I'll call this 1, 2. 1, 2. 1, 2. 1, 2. More or less, that's what's going on here. My art is not perfect, but it's a circle, centered at the origin of radius 2. And the point square root of 2 comma square root of 2 is right here. There's a bunch of ways to think about it. The X and the Y are equal here. So, you know, you have to be at like this 45 degrees. And that's another way to think of how we got the T value out that we did. So my tangent line is this guy. This is the tangent line that we found. Y minus root 2 equals negative X minus root 2. Root 2 comma root 2, this is our point of tangency. I was asked to revisit how we found the pi over 4, that value for t. All right, this is the point associated with t equals pi over 4. So I want to go back and look at that system of equations and see what the other things that we found there would correspond to. So when I set the x equation equal to 2 cos t, I'm sorry, when I set the x equation, which is 2 cos t equal to root 2, I got these two solutions, pi over 4 and 7 pi over 4. The 7 pi over 4 solution is right here. And you see the x value here is the same as the x value here. So there's 2 points on the curve where the x value is equal to root 2. This down here is the point associated with t equals 7 pi over 4. Which was this guy. Similarly, when I set the y equation, 2 sine t equal to root 2, I found two values. Here's the other point on the curve where y is equal to root 2. So this must be the one corresponding to t equals 3 pi over 4. So when we went to find our t values, we had to solve this like as a system because I needed to make sure that x and y were both at the same time equal to the square root of 2. There's two places where y is equal to the square root of 2, and there's two places where x is equal to the square root of 2, but there's only one place where they're both equal to the square root of 2, and that was my point of tangency. Okay, great. Any questions on how we found this tangent line or how we were able to sketch the curve? Okay. So the other day, we found some maxes and mins for the cycloid, which was a pretty challenging problem. I want to look at an easier one, and I want to kind of revisit what we mean by min or max in this context. in Calc 1, we learned a handful of things. There's actually like 3 sections that relate to mins and maxes. There's the section 4.1 on extreme values and the extreme value theorem, section 4.3 on how derivatives affect the shape of a graph, and then section 4.7 on optimization. The gist of all 3 of those is that tangent lines, sorry, I should say this, mins and maxes on curves y equals f of x come from critical numbers for f. Critical numbers are inputs where the curve has, I should say, or might have, either a horizontal tangent line which I will abbreviate as HTL, or a vertical tangent line, which I will abbreviate as VTL. And these are places, so a horizontal tangent line means that the slope of the tangent line is 0. So this means that dy dx is 0. And a vertical tangent line means that dy dx is undefined, specifically that dy dx, the slope of your tangent line, is tending to either positive or negative infinity. And the same is true of parametric curves. The things we would want to call mins and maxes, tallest points, lowest points, leftmost points, rightmost points, come from horizontal and vertical tangent lines, and that horizontal and vertical tangent lines are still associated with dy dx being 0 or dy dx tending to infinity. So I want to draw for you a very general looking parametric curve and sort of just point to the things that I would want to call a min or a max in some sense. So maybe my initial point is over here. My terminal point is up here. And let's say the orientation for the curve then is something like this. The points that I would want to call either a min or a max are like this guy down here, right? If I was to zoom in and look just at this part of the curve and pretend like we're in Calc 1, then I would call that a min. Similarly, up here, if I was zooming in and looking at just this part of the curve in Calc 1, if I gave you that picture and I said point to the max, I think everybody would point to that guy. This should be a min, this should be a max. Another kind of interesting thing stuff like this. this would be a min for the x values. It is the smallest x value anywhere on this graph. And the tangent lines at these places are either horizontal, like here, 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 or vertical, like they are here. So these sort of interesting points, this would be like a min y value, and these two are max y values. And this guy would be a min x value. Correct. And when I say min or max, I mean local min, local max. The way we can go about detecting these things is the same thing that we did in class on Wednesday with the cycloid. We're going to calculate the derivative dy dx as a function of t, just like we did on the tangent line problem a second ago. And then we're going to find where that derivative dy dx is either 0 or blowing up to infinity. So this is sort of the intuitive thing that's going on. Let's actually try to do it. Sorry, there's one here that I didn't label. This fellow would be a min y value as well. Okay, so how do we find these things? In theory, we know we just need to solve these equations. But in practice, let's give it a shot. Let's see what that looks like. So I'm going to phrase it like this: find the location, and by location I mean ordered pair x comma y, where the parametric curve x of t equals t cubed minus 3t, y of t equals t squared minus 3. Oh, is it t squared minus 3? Well, it might be t squared minus 2. Sorry, give me 1 second to check. I'll turn this off because I don't want to give it away. I'll throw this into decimals really quick. Oh, this is good. Yep. All right. Turn the share back on. Here we go. Well, I find where this bad boy has horizontal or vertical tangent lines. And then we're going to say classify each point as a min or max x or y value. All right, we know what to do. Horizontal tangents, vertical tangents. horizontal tangent lines, these come from dy dx being 0. So I'm going to calculate dy dx using dy dt and dx dt. dy dt is 2t, right? I just take the y function and differentiate with respect to t. Dx dt, if I differentiate the x function with respect to t, I get 3t squared minus 3. So dy dx, I know should be dy dt divided by dx dt, which is 2t divided by 3t squared minus 3. So over here, we'll tuck away the calculus, actually do the differentiation, because we're going to use that in each of the other two pieces here. Dy dx will be 0 if and only if this fraction is 0. I want to issue a word of warning, and you saw this with the cycloid the other day. If you go online and watch YouTube videos, or if you talk to tutors at the teaching center even, it is possible that they will tell you, to find horizontal tangent lines, just set dy dt equal to 0. That will work most of the time, but it will not work all of the time. If you want to find horizontal tangent lines, what you really need is dy dx equal to 0, and I want to see you writing the whole thing equals 0. It's true that if you have a nice simplified clean fraction, then the fraction will only be equal to 0 if the top is 0, or if the bottom is infinity. So you need to be a little bit careful. Setting the top equal to 0 will work fine here because the bottom is a polynomial. It's never equal to infinity. It never blows up. But I want to see you writing this whole thing. And if you don't, it's entirely possible to miss solutions. So what I'm saying is, please just follow the recipes I'm giving you here. Horizontal tangent lines, like we said on the previous page, come from setting dy dx equal to 0. In this case, that is the same as saying 2t is equal to 0. So we get t equals 0. dy dx, the slope of my tangent line, will be 0 when t is equal to 0. We were asked to find the location, x comma y, where these things happen. I've just learned that there is a horizontal tangent line on this graph when t is equal to 0, but that does not tell me the point. So the point with the horizontal tangent line is we're going to plug 0 into both of these equations. It's x of 0, comma, y of 0. X of 0, if you plug 0 in here, you get 0 cubed minus 3 times 0, that is 0. Y of 0, if you plug 0 in for t here, you get 0 squared minus 3, that's 0 comma negative 3 for our point. So here's your answer for the first part. Horizontal tangent line happens once at the ordered pair, 0 comma negative 3. Okay. Any questions on how we got the derivative dy dx here? Let's start over here. Any questions how we solved the equation dy dx equals 0 to get the t equals 0 here? So I calculate dy dx. That's 2t divided by 3t squared minus 3. So dy dx is equal to 0 if 2t over 3t squared minus t is equal to 0. The algebra step from here to here, if you want to think of it as multiplying both sides by this denominator, but I urge you to not think of it that way. I urge you to just ask, when is this fraction equal to 0? And the answer to that question in general is when the top is 0 or when the bottom is infinity. Since this bottom is never infinity, the only time this fraction is equal to 0 is when the top is 0. If you have a fraction made up of real numbers, right, neither the top nor bottom being infinity, then the only way for that fraction to be 0 is if the top is 0. So I set the top to 0, and 2t equals 0, divide both sides by 2, get t equals 0. So that tells me I have a horizontal tangent line at the point on the curve associated with t equals 0. And my last step is to find that point. So what is the point where t is 0? Well, I take the x and y equations and I plug 0 into both of them, right? That point is going to be x of 0, comma, y of 0. The point on the parametric curve where t is equal to 0. Plugging 0 into the x equation gives me 0 cubed minus 3 times 0, that's 0. So x of 0 is 0. Plugging 0 into the y equation up here gives me 0 squared minus 3, that's negative 3. So y of 0 is negative 3. So we solve this equation, we get t equals 0. We plug t equals 0 back into both of these, that gives us our point. I calculated those over here. So dy dt is the derivative of the y function, right? Y is t squared minus 3. If I differentiate that with respect to t, I get 2t minus 0, which is just 2t. To get dx dt, I take this x equation and I differentiate it. So if I differentiate t cubed minus 3t, this piece becomes 3t squared, and this piece becomes just 3. So we get the 3t minus 3, and then I divide them according to the formula from the previous page. All right, let's find the vertical tangent lines. A vertical line you can think of as a line with infinite slope, right? Let me turn this on for a second. Right, if you think of a line, here's slope 0 when it's horizontal, slope 1, slope 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, blah, 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 slope 1 million, infinite slope. So a vertical line is a line with infinite slope. If I'm looking for a vertical tangent line, that means I need the slope of the tangent line to be infinite. The slope of the tangent line is dy dx. So to find vertical tangents, we try to find places where dy dx is blowing up to infinity. That means I need 2t over 3t squared minus 3 to be blowing up to either plus or minus infinity. Fractions are 0 when their top is 0. Fractions blow up to infinity as the bottom goes to 0. Right? Think about like 1 over x squared. As x goes to 0, both of those go to either positive or negative infinity. So this will happen when 3t squared minus 3 goes to 0. And since this is a polynomial, we can just set this equal to 0. I'll factor out the 3. Factor t squared minus 1. And we get t equals plus or minus 1. So the slope of my tangent line, dy dx, will blow up to infinity when the denominator, 3t squared minus 3, goes to 0. That denominator will go to 0 as t goes to plus or minus 1. So when t is equal to 1, dy dx is blowing up to infinity. When t is equal to -1, dy dx is blowing up to infinity. So there's 2 points here, or at least there's 2 t values here. And we want to find the points associated with each of those t values. Draw a little partition here. So VTLs are at the points coming from I'll put t equal to -1 here, and I'll give myself some space, and t equals +1 here. Just like before, I need to find the point associated with this t value. So that's going to be x of -1, comma y of -1. So what is x of -1? If I plug -1 into t here, I get -1 cubed, which is -1, minus 3 times -1. So that's -1 minus -3, or -1 plus 3, which is +2. In other words, x of -1. I'll write it here. -1 cubed minus 3 times -1, which is -1 plus 3, which is 2. Let me do it this way, that way I can keep everything nice and big. The y coordinate is going to be y of -1, which is -1 squared minus 3. -1 squared is +1, so this is 1 minus 3, which is -2. So that first point with a vertical tangent line is the point 2, comma, -2. And then to find my last point, again, what I'm looking for here is x of 1, comma, y of 1. So I'll calculate x of 1. That's 1 cubed minus 3 times 1, which is 1 minus 3, which is -2. So the x coordinate here is -2. And the y coordinate, y of 1, that's 1 squared minus 3, which is 1 minus 3, which is also -2. So there's our last point. So these are the 3 points where the tangent line to this curve is either horizontal here or vertical at these 2. I want to classify each of these as being a min or max, x value or y value. There's a few ways to do this. If you remember your first derivative test, you could apply those, but I think it would be nicer here to sketch the curve. This is a pretty wild looking curve. I would not expect you guys to sketch this curve on your own, but it is something I want to show you because it's quite cool. Let me tick off the important values here so I know 1 and 2 along the x-axis are important. -1 and 2 along the x-axis are important. -1, -2, -3 along the y-axis are all important. So the points we found were 0, -3. That was my horizontal tangent. And -2, -2. +2, -2. These were my vertical tangents. The curve goes through the origin twice. If you set x and y equal to 0, you find 2 places where we pass through the origin. If you plug in a few t values that are negative, you'll find your curve starts off over here, comes in like this, loops around, and comes out like this. So we cross through the origin twice, once on the way in, and we do something, yeah, modulo my bad art, something like this. Shouldn't be dipping down, and maybe it's too shallow, but something like this. This is the curve. And the orientation is like this. So this guy I would classify as a min y value. This would be a max x value, and this would be a min x value. Now, like I said, I don't expect you to be able to cook up this curve on your own. I just wanted to show it to you. How could I know then that this is a min y value or this is a max x value without doing that? The answer is the first derivative test. We could use the first derivative test from Calc 1. So these guys came from, put the t values here. This was t equals -1. This guy came from t equals 0. And this guy came from t equals 1. The x equation here was t cubed minus 3t, and the y equation was t squared minus 3. The first derivative test says if you go from decreasing to increasing, that had to be a min. And if you go from increasing to decreasing, that had to be a max. So let's look at this guy. Actually, let's look at this guy first. dy dt was 2t. So if you make a little number line here, where these are t values, and you plot the critical number t equals 0 for dy dt, to the left of 0, dy dt is negative, and to the right of 0, dy dt is positive. So that means my y values are decreasing over here, and my y values are increasing over here. So my y values went from going down to going up, which means this had to be a min. A min y value. I can do the same thing with dx dt over here. Dx dt, remember, was 3t squared minus 3. And if I draw a little number line for dx dt, plotting the two critical numbers that he had, which were -1 and +1, we know at t equals 0, this guy is negative. And then because this is a quadratic, when you go off to the left or the right, the lead coefficient is positive, which means this guy will be positive. Or you can make a sign chart. You could test t values however you want to do it. That means over here, my x values are increasing. Means in here, my x values are decreasing. And over here, this means my x values are increasing again. So if your x values go from increasing to decreasing, that must be a max x value. And if you go from decreasing to increasing, that must be a min x value. And is that what we found? Well, when t is -1, we had a max x value. Yeah, that's correct. When t is -1, we had a max x value. And when t was +1, did we have a min x value? Yeah, when t is +1, we have this min x value here. I am primarily concerned with, and you should be primarily concerned with, just finding these points. Finding the points where the tangents are vertical or horizontal. Make sure you can do that. This is a fun little insight, but it's not something that I'm going to test you on necessarily. It's just something I want you to be aware of. If I was teaching this class maybe at MIT or Caltech or something like that, then I would really put you through the ringer on this other stuff, but not this time. I just want to remind you what the first derivative test you learned in Calc 1 says and how it can be applied here. Questions on finding the vertical and horizontal tangents on any of these steps? Okay. The last thing I want to talk about here today are areas bounded by parametric curves. And I want to very briefly sort of revisit what you learned in Calc 1 about finding areas using integrals so that we can generalize it. So to find the area bounded by a curve y equals f of x, something like this. Maybe from x equals a to x equals b. Right, to find this area. You would integrate the integral from x equals a to x equals b of f of x dx. The thing I really want to drive home, I mean, you say I wrote it twice on the page here, is that the way the graph of a function is defined is that y is equal to f of x. What that means is that the y value on the curve here is equal to f of the x value. So this is the same thing as the integral from x equals a to x equals b of y dx. Right? It's just that y is f of x along the graph of a function. That's what that shit means. Every time you saw that written, that's why. We can do the same thing with parametric curves. So I'll say y is y of t, and x is x of t. And I'll give myself a little parametric curve here. The idea now is that this could be quite a wild apparatus. Maybe my initial point is down here. My terminal point is over here. And maybe I want to find the area between here and, let's say, here, bounded by this curve and the x-axis. So I want to find this area. Right? I'll say that this point is the point associated with the t value alpha, and that this point is associated with the t value beta. Well, the area here is the same thing. You have to integrate from t equals alpha to t equals beta of y times dx. You're still thinking of splitting this region up into a bunch of little tiny rectangles. Each one of those little tiny rectangles has a height, which is a y value, and a little tiny width, which is dx. It's just that y isn't equal to f of x here. Y is equal to y of t. And x is no longer my input variable, so I need to write dx in terms of t as well. So this is going to look like the integral from alpha to beta, which are t values. Y is not f of x, but it is y of t. And if x is x of t, then dx, calculate your differential, that's x primed of t times dt, very similar to when you do a u sub. So your dx here is x primed of t times dt. So this is your formula to find the area bounded like beneath a parametric curve, bounded by a parametric curve and the x-axis, like so. You can also find a formula for areas like this that are bounded by the curve and the y-axis, and I'm going to show you that in just a moment. Okay. So this is the area bounded by the parametric curve and the y-axis. Sorry, and the x-axis. We do require one thing, and that's that the curve be kind of well behaved between these, right? That the curve doesn't double back on itself or do anything crazy between these two t values. There needs to be a reasonable area here to discuss. The similar looking recipe to find the area bounded by a parametric curve on the y-axis, and I'll draw you a picture. I have a parametric curve. I'm doing something like this. Who knows? Could do whatever. Push a point here. Terminal point here. If I want to find maybe the area bounded between my curve and the y-axis from, I'll call this t equals alpha, and this t equals beta, then I can calculate this area. Let's see how I'm going to show this carefully. I can find this area. By sort of turning the picture sideways, right? Here's the lower bound. Here is the upper bound. And this area we would find as the integral from t equals alpha to t equals beta. Now I'm thinking of x as a function of y. So my little Riemann rectangles would go in like this. So this would be the integral of x dy. which would be integral alpha to beta. X is x of t, y is y of t, so dy would be y primed of t dt. This is the area bounded by the parametric curve. And the y-axis let me see if I can get these two up simultaneously. Here we go. This right here just said x equals x of t. I can put a similar thing here. Y equals y of t means dy is y prime of t dt. So I would like to do one calculation here before I let you guys go. I found a problem that was looking pretty fun in the textbook. I'll go ahead and do that. Where was he? This up on my last. We'll talk about that later. Tangent. And where's the area stuff? I know there was an area. Here it was. Yeah, find the area bounded by this one, t squared minus 2t and y equals root t. All right. Okay. So the curve here, if we want to sketch this, we can eliminate the parameter. We know that y is equal to the square root of t, which means that y squared is equal to t. And also that y is positive, right? Because this is the positive square, it never spits out a negative number. So x would be t squared, which is y squared squared, minus 2y squared. In other words, x is y to the 4 minus 2y squared. So this is a polynomial in y of degree 4. The full graph of this apparatus, if you factor that, use the tools of pre-calculus here, this is y squared times y squared minus 2. I'm sorry, times just y minus 2. Oh, no, it is y squared minus 2. Sorry. Let me rewrite it. This is y squared times y squared minus 2. So you've got a root at y equals 0, and you've got roots at plus and minus square root of 2. And as y increases, x increases. So this is going to look something like cross here, bounce here. The same sort of thing on this side. And we only want the portion of this where y is positive. So we're going to take the upper half, this part, as our parametric curve. When t is 0, we're starting at the origin, and as t increases, y increases. So this is the orientation of the curve. I'm going to draw another version of this down here that just has the part we're interested in. So the area, the region whose area I'm trying to find it's this part, right? Here's my curve with the orientation arrows. So I'm looking for this area. The points that sort of bound that region are these 2 points. And I need to find the t-values. Now I'll put them in. So I'm looking for that area. In order to find that area, I'm going to set up the formula for the area bounded by the curve in the y-axis, but I need to know from where to where. What are those t-values? So how can I find the t-values at this point and this point? What equation would I solve? Excellent. We're along the y-axis here, which means x is equal to 0. All right, this is the y-axis, this is the x-axis. So we need to solve x equals 0, which means t squared minus 2t is 0. Factoring, let's t times t minus 2 equals 0. So we get t equals 0 and t equals 2. So this is the point with t equals 0. This is the point with t equal to 2. Now I can set up my integral. partition here. So that area will be the integral from, I'll write the formula, alpha to beta of x of t times y primed of t dt. That's the integral from 0 to 2. X of t is t squared minus 2t. Y primed of t, so this is t to the 1/2. If I differentiate, then y primed of t is 1/2 t to the negative 1/2. So 1/2 t to the negative 1/2. And then we've got our dt. Popping out the 1/2, distributing the t to the negative 1/2. Gives me this. And then we can apply our power rule. So I'll get 1/2 t to the 3/2 is going to become 2/5 t to the 5/2. Adding 1 to the power and dividing by the new power. T to the 1/2 would become 2/3 t to the 3/2. So with that 2 there, it's going to be 4/3 t to the 3/2. And we evaluate that from t equals 0 to t equals 2. And when you plug in that lower bound of t equals 0, everything becomes 0. So this is just going to be 1/2 times 2/5 times 2 to the 5/2 minus 4/3 times 2 to the 3/2. And that's it. You can distribute your 1/2 if you want. So you get 1/5, 2 to the 5/2 minus 2/3 times 2 to the 3/2. There's more you could do with this. But this would be an acceptable answer. You could stop here. Do I expect this area to be measured as positive or negative, and why? Definitely, if I'm just referring to it as an area, I would want to say that this is positive. The reason I mention this is because the x values along the curve here are all negative, right? Just like a normal integral takes area beneath the x-axis and measures it as negative, this integral is going to take area that is to the left of the y-axis and measure it as negative. So this is actually a negative number. All right, we can Desmos it up for a minute. All right, and I expect it to be negative because this number is measuring an area that is to the left of the y-axis, wherever all the x's here are negative. So if we're asking strictly for the area bounded, we would want to negate this to make it positive. But for the purposes of our problem, I want to make sure you know how to set these things up. Make a little note here. So in order to make that value positive, we would negate it because it is already negative. But if you were to crunch this out for me on an exam, I would not take off points for that. I would be happy with that. I would just make a little comment here. All right. This is where we're going to stop for today, right? We've learned everything there is to know about tangents, mins, maxes, and areas in the context of parametric curves. The beauty of the area problem here with parametric curves is that you can solve some problems that are either very difficult or straight up unapproachable in the normal setting. Specifically, one problem in your homework set asks you to find the area of an ellipse. Work that one carefully. That's a really good problem. I used to put it on exams, and it shows up from time to time still on exams. So finding the area of an ellipse that's given through parametric equations is a fun little problem that I think you'll enjoy. Besides that, I don't really have any comments for you on this week's homework. Just work the problems. If you get stuck on anything, come talk to me in office hours, send me a Canvas message, an email, whatever. I had a shitload of extension requests that I've been granting through the week. If you are behind on the homework, please take the time to get caught up. Specifically, make sure you are very comfortable with the power series stuff. So as we get closer and closer to exam 3, make sure that you are getting comfy with the power series stuff. Oh yes, exam 3. So your guys' final exam, let's do this for just a second. Your guys' final exam in this class here is on the 27th, which is Wednesday at the end of the month, right? The last Wednesday in April. So next week, next Monday, I'm going to talk to you about arc length and surface area. And that will be the end of section 10.2. And then Wednesday and Friday, we will introduce polar coordinates. And then Monday and Wednesday, we can really finish everything if we want to by Friday. Monday and Wednesday, we'll get a little bit more practice. I'm thinking exam 3 will be on the last regular day of class, which is the 22nd. And then your final exam is going to be on the 27th. Now, you may have noticed I posted a review for the final exam. Those are not new materials. Those are materials I made a long time ago when I was teaching at UF. But the content is the same, right? So they are good reviews that I made when I was working for the class teaching center over there at the university. And working those problems is a great way to prepare for the final. Before you get into that headspace of cramming for the final, make sure you're ready for exam 3. So exam 3 for us should be on the 22nd. Let me make sure I've got that date right for the last day of class. Where is it? Here, yeah, 4/22. So exam 3 will be on the 22nd. That is the plan. And it will cover power series and all of the applications of power series, parametric equations and calculus with parametric curves, and then polar coordinates, which is what we're going to start talking about next week after we wrap up the arc length and surface area stuff. Any other burning questions before I let you guys go? Okay, then that's it from me. I hope you guys have a lovely rest of your day. Please work hard on that homework, get caught up on anything you need to get caught up on. Pay special attention, I'll say it again, pay special attention to the power series stuff. Make sure you're very comfortable with like finding intervals of convergence, understanding testing endpoints, the symmetry associated with the IOC, calculating power series by integrating and differentiating, the geometric series trick, and those Taylor series that we were calculating. That's it from me. I'll see you guys on Monday.